Okay, calculus BC. All right, Calc BC, Unit 3, Day 6. Book assignment, office hours. These were the problems. You should check the odds in the back of your book already, so I'm not going to be sharing those right now. This is just our normal book. I went ahead and got rid of a couple problems if you've seen some other version that had more problems. So the first two problems, let's see. In these it says, match the parametric equations with their graph, state the approximate dimensions of the viewing window, give a parameter or interval that traces the curve exactly once. So number one was this. This is like multiple choice, but all right. So if we, I think you want to be in parametric mode for this. Probably the only time we're going to, but yeah. So parametric mode, you go to y equals, and you can enter these in 3 sine 2x, and then 1.5 cosine x. Now there's a pattern that we want to go to window, and I mean, we could say negative 10 to 10, negative 10 to 10 to start with, but then t, min and max, it's time. So usually like 0 to pi or 0 to 2 pi will give you a full shape. We'll just try 0 to pi first. So then we're going to graph it. And the window definitely looks too big. So I think we go like negative 3 to 3. I mean, you could do zoom fit. Zoom fit, zoom 0. So that'll give us a nice close-up version of it. Now, maybe the pattern goes further. So go to window, and maybe you could go to 2 pi. 2 pi is often going to be what it takes to get a whole pattern. And then it looks like it would repeat. And you could confirm that by going to like 3 pi. And we get the same thing that we got at 2 pi. And then we don't see anything because it's tracing over itself. So anyways, that is option C. We could just draw a quick sketch of it. Kind of looks like that. And they said to state the approximate dimensions of the window. So you could go to window after we did zoom fit. It's negative 3 to 3, negative 1.5 to 1.5. So negative 3 to 3 interval for x, and negative 1.5 to 1.5 for y. The parameter, it says parameter interval, so that's the time interval. So for that, we said, I think we figured out it was 0 to 2 pi to get that full shape. Traces the curve exactly once. Okay? So number 3, try this one. I'm going to just write the problem down first real quick. Okay, I'm going to just type this in. So go to y, 7 sine, and put the x, but it gives you a t, minus sine 7x, and then this one's going to be 7 cosine x, t, minus cosine 7t. Okay, now the window, I don't know how big the window needs to be. I'm going to go back to negative 10 to 10, negative 10 to 10. And, you know, I mean, we could start with 0 to 2 pi. That's, you know, likely often. We graph it. So it's kind of a cloud looking shape. We could do zoom fit just to get really nice window, because that's one of the things that we're being asked to do. Takes a little while. So I'm going to just draw a quick sketch of this, and there should be one of those options should look like this. So it's like that, like that, like that, like that, like that, like that. The window, and that's option D, right? So the window, if we go to window, we did zoom fit, it's -8 to 8, and negative 7.39 to positive 7.39. So I'm going to go window, -8 to 8 in the x direction, negative 7.391 to 7.391. The y direction, the parameter. Now it looks like it did trace the whole shape, like it connected and it was going to just probably go over itself again. You could verify that by going to Tmax and saying something like, 3 pi. And so when we did 2 pi, it stopped right there and then it's keeping going. So it seems like 2 pi was enough, got the whole shape, and more than 2 pi would just do it again. So there you go. Now for the other problems, I don't think we're going to be in parametric mode. But, well, I don't know. We'll see. Yeah, these ones I want you to do without a calculator, the way we did in class. So problem 5 was x equals 3t, y equals 9t squared, and time is -infinity to positive infinity. And so it says, A, graph the curve where the initial and terminal points of any indicate the direction of the curve is traced. Find the Cartesian equation for the curve that contains a parameterized curve. What portion of the curve? Graph the Cartesian equation is traced by the parameterized curve. Okay, it's everything we're doing in the notes. So I personally think it's easier to find the Cartesian equation first because that helps you graph it and just makes more sense of everything. So on these ones, we're not doing, there's no trig involved, so we can use like substitution. You're going to solve for t equals x over 3, and then plug that into the other equation like a system of equations, trying to eliminate the t's and get y in terms of x. And so we get y equals x squared. That's your Cartesian equation. So that's part B. And we're going to make a table. T, x, y. Now this goes -infinity to infinity, so probably not going to have initial and terminal points because the graph probably goes on forever. Probably going to get the whole parabola. I mean, we could plug in a couple points. 0 is going to be, x is going to be 0, y is going to be 0. -1 is going to be -3, +9, +1 is going to be +3, +9. Infinity, -infinity is going to go to -infinity. That's going to go to positive infinity. Positive infinity, that's going to go to positive infinity. Positive infinity. So the graph is parabola. So but let's see. It's kind of interesting. Negative. No. Okay, this makes sense. So 0, 0 is point. -3, +9. 4, 5, 6, 7, 8, 9, which totally makes sense. That's the shape of a parabola, right? 1, 2, 3, up 9. The -1 and 1, those are the t values. And we're graphing these on a Cartesian graph. So graph kind of looks like this. Usually I do this lightly, but it's going to be the whole graph. You got to put arrows on the ends. It's going to be the whole graph. Now, we figure out the direction. So it's going from -1, -3, 9. It's going this way. Okay, the arrows on the ends of the graph don't indicate direction. They just indicate that the graph keeps going. So we need the direction on the graph. Initial and terminal points. There is no initial or terminal points. So that's part of our answer. And it is, it says to what portion of the graph. So it's the entire parabola is graphed. So something like that. And then let's see. Next one's number 7. X equals t. Y equals the square root of t. T is greater than or equal to 0. All right, let's try that one out. So let's see. We can just plug that in for t. So y equals the square root of x. That's the Cartesian equation. That's a square root function. That's the inverse of a squared function. So it's the inverse of a parabola. So it's going to look like parabola graph flipped across y equals x. It's just the top half. So I mean, we could you could plug some values in. You can't plug negatives in because it's imaginary. 0, 0 though. 1, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So 4, 2. So this is just the shape of the graph. So then we're going to make a table. And we have 0 is an endpoint, and then positive infinity, I guess, is the other one. Plug 0 in here, you get 0, 0. So that's your initial point. I want it labeled on the graph. I want you to write this next to it on the graph, and then we'll also write it separately and box it. If you go to infinity, it's going to go to infinity and infinity, which makes sense to graph as x goes big, y gets bigger and bigger and bigger. We can plug 1 in and be 1, 1, which you saw that. So the graph looks like this. It's going to keep going forever to the right. The direction is it's going from this side to that. So we add an extra arrow showing direction. This arrow does not indicate direction; it just indicates the graph keeps going forever. This solid dot right here stops. So the initial point is 0, 0. The terminal point is none, or something like that. And it's the I mean, I don't know, there's different ways to describe this. I mean, you could you could say it's x equals y squared. It's just the upper half, right? Or we could say it's y equals the square root of x, all of it, entire thing. I don't know, something like that. Okay, number 9. Number 9 has some of this trig in it. And so we talked about how to get the Cartesian equations. Usually these are going to be conic sections. And so we use the Pythagorean identity, trig identity, sine squared plus cosine squared equals 1. And then, so sine is y, and then you're going to square it. Cosine is x, and you're going to square it. So the equation, probably in its most common form, would be written like this. It's a circle. And so we could start by we could draw a quick sketch of this circle. It has a radius of 1. So usually, best way to draw circles, get a couple points. I'm going to lightly graph it. Okay. All right. So then we can make a table. And we plug 0 and 2 pi into it. If you plug 0 in here, you get 1, 0. So this is your initial point. One, 0. And 2 pi would also be 1, 0. So this is also your terminal point. It would help to probably pick some points in between to confirm what direction it goes around, or if it does go all the way around or whatever. So I'm going to do pi real quick. Cosine pi is -1, 0. So this is another point on the graph. And we do pi over 2. Because still at this point, it could go this way or it could go this way. So pi over 2 would be 0, 1. So that's up here. So it's definitely going from here to here. And it's going to go around the whole circle. And I think it just goes through it once, right? Finding some of these circles can go through once in a matter of just pi. So draw an arrow showing the direction. So the initial point is 1, 0. The terminal point is 1, 0. And it's this, it's the whole, oh shoot. Did I write the problem down? Oh, it's pi. Ooh. So we actually don't get to here. The terminal point is at pi, which is over here at negative 1, 0. That's the terminal point. So terminal point is negative 1, 0. It's not going to be this. It's gonna go this direction. Okay. But then it stops. So it's only upper half of the circle. So we could say it's x squared plus y squared equals 1, upper half or something. You could say that, or you could say it's y equals the square root of 1 minus x squared if you were to solve for y explicitly. You could say that. So there's some different ways of interpreting that. Okay, so that one was interesting. Not the whole shape. I would have graphed it lightly and just darkened that top in. I wrote pi, but I just started writing 2 pi in my work. Okay, so 13 is x equals 4 sine t, y equals 2 cosine t. T is between 0 and pi. And okay, so first thing I'm going to do, so we're going to use sine squared plus cosine squared equals 1. So sine is x over 4, and then it gets squared, including the divided by 4. Cosine is y over 2 squared. So this is going to be x squared over 16 plus y squared over 4 equals 1. And this is our Cartesian. Well, this is what we would usually write as our Cartesian equation. You could solve for x in terms of y, y in terms of x, whatever. But this is an ellipse, right? So I'm going to go ahead and graph the ellipse. We've had practice with this recently. So we're going to go up, right for 1, 2, 3, 4, 1, 2, 3, 4, up 1, 2, 1, 2. You could draw like a little box if you want to kind of help you sketch it better. I find that semi-helpful. Kind of makes it easier to get the shape right. Okay, now I suspect that we might not get the whole shape because we're only going pi here. So if we do 0, I usually leave some room here for the values. Maybe I'm going to do some in-between values. So 0 is going to be 0, 2. So this is actually the initial point right here, 0, 2. So that's the initial point. And if we plug pi in, it's going to be 0, negative 2. So that's going to be over here, 0, negative 2, terminal point. Okay, so now at this point, we do need at least an in-between one, because is it going this or is it going like this? So if we plug in pi over 2, sine of pi over 2 is 1, so that's going to be 4 comma 0. So it's going to end up going over here to 4 comma 0. So I think it's going like this is the terminal point. And so this one is interesting. It's only half the shape. Also, the direction is going clockwise instead of counterclockwise. So we've seen that last example, it's going So minor, things. You'll notice x had sine here, and x on the last problem had cosine. So it makes a difference in the direction. That's one effect, or maybe which half. So let's see. Initial point is 0, 2, and terminal point is 0, -2. And we could just go up here and say, okay, it's the right half of the shape of the ellipse. So there you go. All right, 15. X equals 2t minus 5, y equals 4t minus 7. T is negative infinity to infinity. So probably not going to have initial and terminal points. Probably it's going to be some shape, all of it forever or something. We'll see. Let's try and solve this. So I would solve for t here. I'd get 2t equals x plus 5, and then you divide by 2, and then you're going to plug this into t for the other one. So y equals 4 times parentheses x plus 5 over 2 minus 7. So y equals 2x plus 10 minus 7 is going to be plus 3. So it's a line, right? It's a line. Last one was an ellipse. Previous one was a circle. Okay, and I think it's going to just be the entire line. So graph our line. So it starts at 3, and then it goes up 2 over 1, up 2 over 1, or down to left 1. So it looks like this. And I'm going to go just make it darker now. Now we should put arrows on the ends, which does not indicate direction. We could do a little table right here, which will help us figure out the direction. Negative infinity, it's going to go to negative infinity, positive infinity is going to go to positive infinity, which makes sense with the graph. And I think that also tells you now the direction is that this is the beginning of the graph, this is the end of the graph. But we could plug in a couple values. 0, it's be -5, -7. Ooh, that's weird. Oh yeah. That's way over here. 1 is going to be -3, -3. So, I mean, we could do 2 is going to be -1, +1. That's that point right there. 3 is going to be +1, 5. That's this point right here. So it's going this direction. So we draw another arrow right there. There are no initial or terminal points. So okay, 17. I'm gonna see if we can fit it right here, just to save a piece of paper or something. So 17, x equals t, y equals 1 minus t. T is between 0 and 1. This one's easy to get by itself. Y equals 1 minus x. Y equals -x plus 1 is a little more common way of writing. It's a line. By the way, the last one is it's all of the line. This is a line, but we actually have restrictions on t, so I'm suspecting we might get a line segment. Okay. So I'm going to graph this line. And it has a y-intercept at 1, and it goes down 1 over 1, or back 1, up 1. So it looks like this, lightly, because I don't think it's going to be the whole thing. Make a table. T, X, Y, 0 and 1 for sure. 0 would be 0, 1. So this is your initial point. And 1 is going to be 1, 0. So this is your terminal point. So I think the graph is just going to be this piece of the line segment, and the direction is going this way. I don't really think we need to do any other calculations. This is the beginning, this is the end. So initial point is 0, 1. Terminal point is 1, 0. And it is a, it's a line segment. Or, or we could say it's part of a line, it's part of this line from 0, 1 to 1, 0. I mean, try and describe what piece of the Cartesian equation is. So there you go. All right, last problem, 23. And I did one like this at the end of the lesson. So otherwise, I'm sure you probably would have felt a little confused about what to do, but it says find a parametrization for the curve, meaning you're being given something and you need to write the parametric equations for x equals this with t's, y equals this with t's, and what are the boundaries for t. So it says a line segment with endpoints from -1 to -3 and 4 to 1. Now, one interesting thing is they don't give me any time requirements, so we can kind of make up our own time requirements. And what we decide for our time requirements will affect the equations we get also. So I'm going to say this is time 0 and this is time 1, just to keep it simple. Okay, so we could do something different, but then it would change our answer. If we said time -100 to 100, you could do that, but then your answers would be different. So I'm just going to keep it simple, 0 to 1. I think that'll make the work easier too. And it'll give a correct answer, but there are multiple correct answers for this. So what we said is, well, x is going to be some kind of linear equation, at plus c is what we used in the notes, and y is going to be some linear equation, bt plus, d or something. I don't know. You can use whatever letters you want, wherever. So we need to find those 4 unknowns, and then we'll pretty much have our answers. So we're going to use time 0 first, probably. Time 0 gives you a, and it should equal -1. So there you go. You got one of your answers. Oh wait, hold on. Gives you c, because the a term drops out. And then y0 just equals d, and that should be the y value there, -3. So now we can rewrite it with those in it and then do it for the same thing. So x at time 1 is going to give you a plus c, which is now -1, and it should come out to 4. So then that means that a equals 5. And then y1 would give you b plus d, which we already figured out was -3, and it should equal a y value at time 1, which is 1. So then b equals 4. So now we're going to write our equation. So x equals 5t minus 1, y equals 4t minus 3, and then you need to include your time constraints, which is what we also, like I said, you're going to get a different answer if you do it differently. So that's one way to do it. You could do it some other ways. I feel like that's a nice, simple way. That's it. Hopefully you're getting pretty good at these common parametric curves.